They say life is stranger than fiction.
There's two ways of going a supernova, and fortunately, everyone can relax. The sun won't go supernova. It will become a red giant, although when it becomes a red giant, Mercury and Venus will probably get swallowed by the sun.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
This is how technical we're now getting. And actually it happened with Interstellar that when it was published, people were working out the time dilation that you just described and were saying, this is wrong. And because they'd missed the fact that it's a rotating black hole.
Welcome to Sci Fi, Sci Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy, if any theory exists. In this episode, Jan Eldridge, Associate Professor of Physics at the University of Auckland, takes a look at the use of supernovae, exploding, but also the opposite, dying stars, as plot devices in fiction.
This is Trans-Soma Medical Rescue Vessel Nightingale 229, hailing Trans-Soma Mining Operation Titan 37. Repeat. This is Trans-Soma Medical Rescue Vessel Nightingale 229, hailing Trans-Soma Mining Operation Titan 37. Repeat.
Were you thinking of any particular science fiction number in terms of this, like some episode of Star Trek, or, you know, the film that I think of, which is not quite supernova, it's kind of the opposite, is a film called Sunshine. Do you know that one, where the sun is dying and they send this spaceship with all the basically all the nuclear weapons we've got to crash into the sun to spark it back into life? Do you know that one?
Unfortunately, I do.
Our sun is dying. Mankind faces extinction. 16 months ago, I, Robert Capa, and a crew of 7 left Earth frozen in a solar winter. Our mission, reignite the sun before it's too late. Welcome to Icarus 2.
And it's a great movie in terms of, you know, the depiction of space, of going to the sun, the special spaceship you need. But the physics of why the sun is dying, I just really, really hate it. And they never explain it in the movie. If you watch the movie, they never tell you why the sun's dying. Until you go to the DVD and you look at the special features and you find out that Brian Cox was a science advisor, I think, and it tells you this on Wikipedia. And he came up with a quantum, like there was some strange particle that got into the center of the sun and it was stopping the nuclear reactions. And it just made me so like, no, that wouldn't happen, because we would see it. We would see stars suddenly vanishing like the sun. And it's just,
really? Not even the great Brian Cox could bring you around.
No. I mean, so he's a particle physicist, so he knows what he's talking about, and it's perfectly reasonable. But it's like we don't see that in the universe. And actually, it's really hard to kill stars, and it's really hard to blow them up. So, you know, I mean, you're talking about Sunshine. There's another movie actually called Supernovae that came out in the year 2000, and it's just like they wanted to blow a star up, and this is. You see this time and time again in lots of science fiction shows where it's like the writer goes, need to blow a star up. And they use magic to try and do it because, yeah, it's annoying.
So Brian Cox hasn't fallen in your estimation, has he, Jan?
No, because he's an excellent communicator, right?
Okay.
And the job he does, that's fine. But it's just in this one case, this one movie, I may never get over it. I'm sorry.
I mean, for me, it's a great movie. I really enjoyed it, and I found it really gripping. It was one of those thrillers that had me on the edge of my seat, and I was uncomfortable. You know, especially when they ventured outside the spaceship, and they had to avoid even though the sun was dying, it still packed a punch, and they had to avoid being hit by the sun's rays because there was something wrong. They had to go out and repair. And that was fantastic. But yeah, I kind of just didn't even think about why is the sun dying, it's just dying, some suns this happens, and then, get some atomic weapons, you can kickstart it again, that could be plausible.
Which is the one thing you would never do. I don't know where they came up with that, because, actually just the center of the sun is like billions of degrees Kelvin, and to actually get the material down there would be nearly impossible. So it's but it's fun. And the other bits going outside, that is real. Even if the sun was dying and you're outside, you would get burnt to a crisp very quickly. That was very well done.
The only supernova story that's coming to mind for me is actually one that it's a short story that Arthur C. Clarke wrote. I think it was Arthur C. Clarke. And it's, I can't remember all the details, but basically these people, I think, know that their sun is going to turn into a supernova, and they're getting ready for the inevitable. And somehow the connection is made between this supernova, and this is a different civilization. It's not Earth. It's another civilization, another planet. And the supernova, and they're getting ready, and that's going to be the end for them. And then it cuts to Earth, and this supernova is the star that guided the wise men to Jesus. Does that ring a bell?
Yeah, I think it's called The Star, I think. And it's like, it was in an anthology, as you say, by Arthur C. Clarke. And yeah, I mean, I've never read this story, but it is that question of like, what would you do in that kind of global catastrophe? Because I mean, there was that recent movie, Don't Look Up, about an asteroid going to hit Earth. And that's the fun thing about sci-fi. Sometimes it's about science, and sometimes it's just looking at society in that way. So, what would you do if you knew we had like years to live, and you would try and leave a record of, I'm sure, of like your civilization? But then also to link it to Star Bethlehem. And I remember there were some people who say maybe that was a supernova or not. We don't know. We can never. It's always difficult to work out exactly where it was and how long it would last. But it's kind of, it's never like it is telling a story about life and the sort of like fragility, I suppose, examining the fragility of life by having a supernova there, and just what it can signify to different civilizations if you're very close up or if you're very far away.
The thing about our own sun is it will become a red giant at some point, but that's not the same as a supernova, is it? No. So then there's two ways of going a supernova, and fortunately, everyone can relax. The sun won't go supernova. It will, as you say, become a red giant, because at the moment it's taking hydrogen, the simplest element in the universe, and turning it to helium. And once it's done all of that, it will eventually get hot enough at the center to take the helium and convert it into carbon and oxygen. And that core then shrinks down and becomes something a white dwarf. And as the core shrinks down, all the remaining hydrogen that hasn't been burnt gets thrown off and falls to something called a planetary nebulae that are really quite beautiful. But of course, as that all throws off, all the planets and stuff will still be left pretty much okay. Although when it becomes a red giant, Mercury and Venus will probably get swallowed by the sun. So eventually sorry, Jan, sorry to interrupt, but what is the part of the sun's life cycle that's, in your opinion, really quite beautiful? What was that again? I didn't quite catch that.
It's a planetary nebula phase.
Planetary nebula.
Because when people used to look through telescopes, they used to think, it looks a bit like a planet, but it's a star very far away. And so it's actually like an ionized gas. So the gas gets thrown off, and you've got this big gas cloud coming away from the star. And at the center, you've got this white dwarf, which is effectively the very hot ashes, the very hot embers of the nuclear fusion that's just slowly cooling down. But in that first phase where the gas is thrown off, it's really hot, and it ionizes this gas cloud, and you see them all different types of shapes, because some of these things are in binary stars, and the material doesn't get thrown off symmetrically. It can get thrown off in funny shapes. And so you can get things like the Cat's Eye Nebulae, things that look like butterflies. And so they can be quite beautiful, and they last for about 100,000 years. But then you get this.
What will the sun look like, perhaps, from Earth in this phase?
Oh, in that phase, well, the Earth will already be cooked.
Really? We'll be cooked by then?
Yeah.
We'll already be gone. Will we have been swallowed by the sun by then, or just simply cooked?
No, you will just be cooked. So in about 200 million years, the sun will be too hot to actually for life to be on the Earth.
200 million years, did you say?
Yep.
Really?
Yeah, that's all we've got.
Really?
Yeah.
I thought we had several billion, Jan.
That's just until the sun becomes a red giant. But the sun is growing and getting hotter, and it's growing at about an inch a year. And so it gets hotter and brighter every time. And so the temperature of the Earth over 200 million years is roughly when we think it will be too hot for life. And so we'll have to move to Mars or to the asteroid belt or further out to be in the habitable zone.
This is a revelation, Jan, that we've got less time. And I thought, we've had about 4 billion years so far, and we've got another 4 billion before the sun starts to go feral on us. You're telling me we've only got a fraction of that time.
Yeah, it's still quite a long time, though.
200 million is a lot less than 4 billion.
Yeah. But
we better start making the most. We better start making the most of this planet. Time is short. It's later than we think.
Yeah, I suppose you could look at it that way. Yes.
Anyway, sorry, Jan. I've gone all off on a tangent. I've got
I've
got my own planetary nebula running around my brain now. Okay, we're already cooked, so we won't even see this. But is this even before the sun becomes a red giant?
No, so it's the time phase. The sun will become such a big red giant that the surface almost just floats away in some ways, of one way of looking at it. And so that gas cloud that we see evolving and looking is like a colourful cloud of gas around this hot star. Will actually be, if there was in a spaceship or something, or if we're on Mars or Saturn or Jupiter, we'd be inside the bubble. And so we would see this gas cloud expanding away from us with this very hot blue-white sun at the centre of our solar system that would slowly then fade away.
Okay, it still sounds like, that is already a great vehicle for science fiction. But it's interesting because I've learned something, Jam. I've learned that it's not just going to go boom, it suddenly turn into a red giant. One moment it's cooking helium, the next moment it's fusing hydrogen into helium, the next moment it's helium into carbon and oxygen. No. It's going to be doing this slowly. We're slowly going to cook. So that kind of, in terms of our own sun, it's not going to be a sudden demise. So we've got to look to other stars for the sudden explosion scenario.
Yeah. So if our sun was in a binary star system and it's become a white dwarf and it's got another star nearby, what can happen is the white dwarf of carbon and oxygen can interact with this other star. And we're not too sure exactly what goes on. We know it's got to be a white dwarf that explodes. But that white dwarf can get to a mass that's about 1.5 times the mass of the sun, because it can steal mass from the other star, or maybe it can collide with another white dwarf. And that's at the point in time when you get this really dramatic explosion. And that's where you make this something that's about 1.5 times the mass of the sun. It's all carbon and oxygen, and it ignites and produces something called a thermonuclear supernova, because it's just a carbon detonation. And it makes about one sun's mass worth of iron in a single explosion. And these are the brightest supernovae, and these are the ones that people use to actually, because they're so bright, we can see them in galaxies billions of light years away. And so we can actually measure the expansion of the universe. But yes, that's also, though, where all the iron comes from. So the iron in your blood has come from stars like our sun that have exploded in this one type of supernova, even though it's not the most common type of supernova, but it's the type of supernova that makes all the iron in the universe. So that's where the iron in your hemoglobin in your blood has come from.
Comes from an exploding star. If it wasn't for supernova, I wouldn't have blood. Well, we wouldn't be here.
Yeah. Well, no, so that's one type of supernova. But then the other type comes from things we call massive stars. And so that's stars that are about 8 times the mass of the sun. And these are so big, their cores can keep on fusing. They go past carbon and oxygen, don't stop there. They go to form neon, magnesium, silicon, and iron. And when they've got this iron core, that can collapse down to that neutron star thing, which is like just a big ball of neutrons. And of course, this thing is still about 1.5 times the mass of the sun, but it's just made of different stuff. And that can blow a star up. And the thing is, that only happens for these massive stars about 8 times more massive than our sun. And those supernovae, because again, it's different. The explosions are coming from a different thing at the center. One thing was a carbon oxygen white dwarf. Here, it's this massive star forming a neutron star, and they make all the oxygen in the universe. So it's not just we need the iron in our blood to live. We also need the oxygen in these exploding massive stars to be able to breathe, for the hemoglobin to have something to carry around our bodies. So that always gets me excited. And so when I see in movies that supernovae are just made up by magic, it really upsets me.
Because you're talking about stars 8 times the mass of the sun. Now, aren't there many, many stars much, much bigger than that in mass?
Well, if I remember correctly, it's something like most stars are actually about the same mass as our sun. So it's actually only about, I'd have to go and actually calculate it, but maybe let's say about 10% of all the stars in the universe are the ones that would actually go supernovae. And you're right, it's from about 8 times the mass of the sun up to the most massive ones, maybe being 300 times the mass of the sun. So it's a really, really big things. And it's just, when they explode and die, output as much energy in a few months as our sun will output over its 10 billion year lifetime.
At the end of a supernovae, what are you likely to have? Are you going to have always have a neutron star at the end of that?
Well, one of the big questions we don't know is we know you get, when this massive star dies, you're either going to get a neutron star or a black hole. But the question we don't know is, we know whenever you form a neutron star, you're going to get a supernova, because you've got lots of energy there, and there's something still there that can then store that energy and put it into the material around it and blow the star up. But with a black hole, we're not too sure, because we know sometimes we see things where it's like that black hole was formed, swallowed some of the material and spat it back out again. But sometimes we've seen at least one, well, we think we've seen one star that has just gone, so there wasn't even a supernova. And so that star died and didn't return anything to the universe, all the material, all the nuclear fusion.
It simply went black. Simply got to a point where its own gravity meant that no light, no energy was emitted from it, or hardly any.
Yeah.
And so that would be going. Are there any science fiction scenarios you know of where that happens, where the sun just goes pop, turns off because it's become a black hole?
Not a black hole, but there are plenty where they try and turn the sun off, and this guy is supposed to go back to sunshine. That's, for example, one case. But there's something called the Saga of the Seven Suns by Kevin J. Anderson. And they have these alien beings that actually live in stars and also in gas giants, and they're at war with each other. And so the beings, or the aliens that live at the very center of gas giants, planets like Jupiter, go and try and destroy a star, because that's where the beings that live in stars were living. And this is told from the viewpoint of humans sitting on a planet where suddenly their star does straight dying, but it's not like in sunshine where it's slowly dying over many many centuries. Here, it's like overnight, the sun shuts down. And again, that's you're kind of appealing to magic and like fantastical beings who have this wonderful understanding of the universe. But it's, when you're looking at it physically, I tried really hard to think of how I could cause a supernova in a star within certain bounds, and it's impossible, because the amount of energy you need is so much.
There are some science fiction scenarios where that happens. Isn't there a Star Trek Voyager? They'd force a star to go supernova. Why were they trying to do that? No.
But they weren't. It was because in Star Trek, there's these beings called Q who are omnipotent. So they're like gods, and they're having a civil war, which is kind of weird, because if you're omnipotent and you're having anyway, and so because they're warring, they're destroying stars.
Why would you? I mean, you'd be beyond warfare. I mean, that's just petty.
Yeah. If only it was all that simple. But yeah, so they have this. So they're wiping out, and so this crew suddenly see 5 or 6 supernova all going off, and think this is a bit weird. And they find out it's just because some gods are having an argument. So yeah.
How much energy would we have to be able to somehow reel in a sun or 2 or 3 and collide them in order to make a supernova? Could that possibly do the trick?
So I worked out in tons of TNT, how many tons of TNT you need to get the energy for one supernova. And it's 10 billion trillion tons of TNT. And so that's more massive than, Jupiter. It's, there's not enough material around, so we can't do it chemically. And so you're right, you'd actually have to probably train to stars around. There is something that some theorists once came up with called a Sakharov thruster, where you build a big shell around your star with a hole in it. And if you balance the gravity just right, you can drag the star away from its orbit, and then you can try and smash 2 white dwarfs into each other. So that would be the best way of doing it. Core collapse supernova is difficult, because you need to have something that become a neutron star. And it's not like you can't take a neutron star and throw it at another star, because it's the formation of the neutron star when it goes from that iron core to the neutron star that causes the explosion. But if you can smash 2 white dwarfs together, you're right. That is one of the, we're pretty sure that's how some of the supernovae we see actually happen. But yeah, if you wanted to, so in the novel Red Dwarf, they have this idea that Coca-Cola want to make a supernova on the sky so that the supernovae write out Coke is life. And so if you wanted to do that, you would have to get these white dwarfs smashing at each other in the right places, in the right patch of sky, all at the right distances, so that from Earth it looks like at the same time. It would be a long-term project.
You're listening to Sci Fi, Sci Fact. I'm talking to Jan Eldridge, Associate Professor of Physics at Auckland University, about the plausibility of, well, we know that supernovae and supernova, they happen, exploding stars, but as I guess the backdrop to science fiction scenarios, but also the plausibility of making them as well. Jan, what about making a black hole?
So that's pretty easy if you've got a neutron star. So we're actually not too sure how big these neutron stars can get. But if you keep adding mass up onto them, they will eventually become a black hole. And we've actually probably seen a few black holes that are like that because they've been in the binary star system. And there's a really good plot device in the recent Expanse novel series. So if you've read that series and you haven't got to the later books yet, turn away because there's spoilers coming up.
Right. Spoiler alert, Expanse fans, block ears, fast forward, whatever.
It's only a few years old. But there's two alien things that are in species that have been in battle. And so one of them decided, okay, let's get this neutron star and spin it up to just below the mass where it becomes a black hole. And what happens is they booby trap it. And so when somebody was to visit them, they go in and they start looking at the neutron star like the aliens might have done. And then it becomes a black hole and actually has these massive, powerful jets and explosions that it's not dramatic, but you would see them if you was looking in gamma rays, you'd get these bursts of gamma rays. And so, yeah, that's actually when I looked at it and I thought like that's brilliant because they were actually taking real physics. They really understood what was going on with how you can take a neutron star and turn it into a black hole. And it was, if you could do that and you find yourself a neutron star, completely physical and reasonable. So it was really quite exciting to read that. Yeah, they haven't made that into the TV series yet, but yeah, so it'd be interesting if they did because it would look fantastic. Jan,
a little aside, I should have asked this earlier, but just remind us again what a neutron star is.
Okay, so a neutron star is, they can go back to the other one we talked about where we talked about neutronium, but it's effectively, it's a star that's about 1.5 times the mass of the sun, but all the stuff is compressed down into 10 kilometers across. So something the size of a small city. And everything is so dense, it's like one giant nucleus, and everything is made of neutrons. So there's no protons, it's all just neutrons, and that's the only way it can be so dense and held together.
No electrons
and it's that
either.
Remnant. Maybe at the surface, it's complicated because, again, it's the extremes of the matter we're talking about are so extreme that we don't really understand them, and we have to start talking about things about nuclear pasta. And this is the last thing we can talk about with all this stuff with science fiction is, with black holes and neutron stars and supernovae, I talk about how can we make one, but in science fiction, what we see is people actually using them. Because, if you've got all that energy around, what better way of trying to do your mad experiment than trying to have all the energy? I've just told you how much TNT it is. And so actually we find that, people are we have the Time Lords in Doctor Who have their time travel because they made a supernova, they had the black hole, and they used that to power all their time travel experiments. So, they're flipping their head on the thing rather than talking about how to make a supernova. It's what can you use a supernova for?
Really? What, the TARDIS is powered by a supernova?
Yeah, I think the original... So there's one case where the Doctor's trying to talk to Rose because she's trapped in an alternate dimension. And so he actually does use because it was the 10th Doctor, he does use the exploding supernova to power the connection through. Whereas, the earlier Doctors actually went through and discussed this, how Omega, the first Time Lord, was a stellar engineer and from a supernova going off, was able to use that to build the TARDIS, understand time, and allow the Time Lords and the Doctor Who and the TARDIS to travel through time.
Okay, well, let's just look at that for a moment. How could you possibly get close enough to a supernova to exploit any of the energy coming off it? And what would you use to harvest that energy?
I would have to go with magic here, because you mentioned right at the beginning about sunshine, how just in front of the sun, they had to go outside and do experiments, and that's trying to fix their ship, and that would have fried them instantly. It would be much worse with a supernova, because it's not just, you've got all these radioactive particles flying around. They would be very bad for you. We know radioactivity is bad. You've got one of the reasons why supernova shine is because they're making radioactive elements that then decay. And so again, a supernovae would not be a nice place to be. But I mean, imagine you had a spaceship with very thick lead walls. Actually, probably if you took an asteroid, burrowed into it, if it was a metal asteroid, you could actually be inside pretty safe, because the metal of the asteroid would probably shield you. And then if you had a magnetic field as well to make sure any charged particles don't come near where you're living, you would be able to sit there. And actually, because there's all these particles coming off, you would actually be able to trap those and try and harness that energy into heating things and actually doing the experiment you want. Or you wait for the supernova to die down. That may take a few hundred years. But if you've got the black hole or the neutron star at the center, then even just being near that, and if you were to try, and if it's a feeding black hole or neutron star, so metallic matter is going in, you get the heat released. And again, that's actually probably a bit safer to do than just using the big explosion. And I think recently some astronomers in Taiwan, if I remember correctly, actually did the same calculation of what happens if you have a black hole, build what we term a Dyson sphere around it, which is a habitable shell where, you try and capture all the energy that comes off a black hole accreting. I mean, you wouldn't want to do it for a supernova because that's really explosive. But the remnant, that black hole or neutron star that's left over, you could use that to power your civilization for a long, long time, just by building.
How come something energy is coming out of a black hole? I thought everything got sucked into the black hole by its gravity.
Yes, good question. So if we go and think about Interstellar. So in Interstellar, they have this black hole they go and visit, and you can see the accretion disk that's very, very bright. And so this is actually real physics. So you've got this accretion disk and stuff is flowing in, but because you've got to take angular momentum away. And the way the disks work is that stuff goes in, but also stuff comes out in terms of material. So it spreads out very thin. It gets wider. So if it starts off thick, it becomes thinner and spreads out. But also it gets very hot because you've got all this stuff rubbing against each other. And so that's where the energy comes out, because it's the energy falling down into the black hole. And of course, the stuff that goes right inside, you never get out. But the process of that stuff forming this disk, because people often think a black hole just goes and sucks stuff in. But, it's the same idea as the planets going around the sun. We don't suddenly go and dive into the sun. We kind of keep going because of this thing called angular momentum, the momentum you've got to go round and round in circles. And so that's how you can actually gain energy coming out of a black hole. You have that accretion disk like you see in Interstellar. And that actually, if the black hole is big enough and the disk is big enough, can produce quite a lot of light and quite a lot of energy that's then released.
Was it Dyson sphere? You said that in theory could be built around the black hole and could capture the energy and could power civilization?
Yeah. Because people have always suggested that there may be these things that are built around normal stars. And what was interesting about this paper I read is that they said, well, why do we just build it around a star? We can build it around a black hole or a neutron star and use that as the energy source.
If we did that, though, say if you're close enough, you'd help. Say, imagine a black hole where the sun is. How close would we have to build the Dyson sphere to the black hole to get sufficient energy to support life?
We would probably actually, if we didn't want to cook ourselves, have to be further out. I would have to actually go and crunch these numbers because it's not an easy thing to come up with.
Right. So
you wouldn't go quite close.
We would have to build a sphere, a massive, like about the size of it would be about as big as the Earth's orbit or more.
Yeah.
Around the sun.
Possibly.
What would we build it out of, Jan?
Well, the rest of the planets. I mean, this is where you have to start appealing to the fact that technologies and materials will develop, but it's very difficult. One of the strongest substances you see within science fiction is this kind of single molecule where you build a spaceship whole out of a single molecule, so it's really tough rather than having lots of things. But again, it's difficult. So
none of this stuff sounds easy. Jan, but the other thing about a black hole, its mass, its gravity, affect time? You know how in Interstellar they get close to the black hole and they think half an hour, they're on a planet that's closer to the black hole than the spaceship that they've come from, the mothership, and they're down there for less than half an hour. They get off the planet because there's some big wave that's going to swamp them, and it actually kills one of them, I think knocks off one of the cast member. And they go back to the mothership, and the only one on the mothership says, you've been gone about 11 years or something like that. Isn't that going to be another issue? If we're this close to a black hole, even say out of Mars, would it change time for us?
It would do, but it's not until you get really close. But then this also depends on whether it's a rotating black hole, or this is how technical we're now getting. And actually it happened with Interstellar that when it was published, people were working out the time dilation that you just described and were saying, this is wrong. And because they'd missed the fact that it's a rotating black hole, because Roy Kerr, who's a New Zealand mathematician, physicist, is the person who came up explaining what's unique about a rotating black hole and how it makes this time dilation worse. But if it was a non-rotating black hole, it wouldn't actually be that bad. But it would mean we'd have to have a spherical shell, right? If you tried to build a tower or something, then there would be, if you went, the people closer to the black hole would be experiencing slower time than those further on out. So that is, again, a huge problem when you start looking at this. But that would only be significant if it was a rotating black hole, rotating close to as fast as the black hole can rotate.
A rotating black hole, why would that dilate time in a different way?
Okay.
Sorry, Jan. All this stuff is so interesting. There's all these various threads. I can't help myself.
I know. Well, before going into that quickly, we don't know how rotating black holes form. Maybe they form we know they definitely do become rapidly rotating when two black holes merge, because if they spin around each other and then come together, and there's a lot of spin that has to go somewhere. So it goes into the black hole. But when stars die in a supernova, we're not too sure if the spinning of the black hole actually has anything to do with how fast the star was spinning. And there's an interesting disconnect there. But to try and describe why the spinning black hole is different.
You haven't prepared for that one, have you, Jan?
No, but the universe is really weird.
Isn't it?
And it's all to do with energy and stuff.
Isn't it? And our time on it is less than I thought. You've taken billions of years off my prospects. Okay, I wasn't going to be around anyway, but, my descendants, they've got less time than I thought. Never mind.
I'm sorry.
Oh, that's all right, Jan. I'll get over it. Last thing I wanted to ask you, supernovae. Say there was a supernova as close as Alpha Centauri or something like that. Would it wipe us out? Are these explosions so big that even stars reasonably close to us, if they went supernova, would they affect us?
So the good news is that there aren't any nearby stars that will go supernovae in the next few 100 million years. So we're safe.
How do we know, Jan? How do we know?
So we're living in a quite remarkable age where we know the distance to nearly all the nearby stars. So we know the nearest 2,000 stars, and that's out to say a few hundred light years. We know the distances, and so we can work out how far away they are. There's two that are going to probably go next, the closest. I mean, any other star in the galaxy might explode, but the two that are closest to us that we could worry about are one called Gamma Velorum and the other one is Betelgeuse, which everyone knows because it's in Orion and it's red and it's easy to see. But if those explode, then we'll see a very pretty light show, but we're probably pretty much okay. We're not too sure exactly how close you'd have to be because so a colleague of mine, Elizabeth Stanway at the University of Warwick, has done some of these calculations trying to work out when our planet became habitable, or because it wasn't going to get killed off by a supernova or something else in the galaxy. And so you have to assume a distance. And it is about a few hundred light years. When things are beyond that distance, we're okay. We'll get a great light show and we'll be able to read at night from the light of this supernova, but it's not going to affect us. But we do know that supernovae have gone off in the years of evolution of the sun because we can find different layers of sediment that are clearly supernova ejected, where the supernova went off a few hundred light years away. And the dust eventually got to us after a few million years and actually then got onto the surface of the Earth. And there was a thick enough layer that we can actually detect that in the sediment layer on the ocean bed.
Could some of those supernovae have been responsible for extinction events on Earth?
Unlikely, because then we would see them linking up with those. If it was going to kill anything, there would be enough material in the fossil record that we'd be able to actually see that for change in the number of the fossils through the fossil history, the fossil record at the same time, and which we don't see.
Betelgeuse already glows brighter and fades a bit, doesn't it? And I know there's been some recent publicity about that, and some people saying, "Oh, this could be a sign it's about to go super." But Alan Gilmore, our regular astronomer, has said, nah, that's not likely. It does naturally change in brightness a bit.
Yeah, those stars do. So all these red giants, and we know red giants like Betelgeuse explode. The first one we actually saw. So we have these images of stars. We see a supernova, we go and check the Hubble Space Telescope archive, see if there's an image of the star before it exploded. And we know Betelgeuse and those stars that look like Betelgeuse do exploding supernovae, and they all vary towards the end of the lifetime. So we know this happens. It's not a link, but when I say the end of their lifetime, it might explode tonight or it might explode in 100,000 years.
What's the last known supernova event that was that bright that, say, you could use it to read at night?
Okay, so this is a really good question because I checked this. It was 1987A that was exploded on February 24th in 1987. So in 2 days' time, it's the 35th anniversary of this naked eye supernova. And you could only see it from the southern hemisphere. So everyone in New Zealand, some of the viewers may be able to remember this, that they would have been able to see the supernova with their naked eye. Okay. I'm really annoyed that I'm still waiting for one.
But that wouldn't have been a so bright you could read it at night event, though. Don't we have to go back a few hundred years for that?
Yeah, so if you go back in history, even those ones like there's the one in 1604 that I think Kepler saw, and then there's Tycho Brahe's supernova, which is from 1500. So some people say we're overdue for a supernova in our galaxy, but it's like about 400 years ago is how far we have to go back.
I seem to remember some accounts from Chinese astronomers of a supernova that ended up becoming the Crab Nebula.
Yeah. So this is interesting. So there is an entire field called archaeological astronomy where they go into the ancient records, and the Chinese records are the best. And so the ones before Tycho and Kepler, we can go back to 1006. I think there's a supernova there. That's how far back they can go for all these different supernovae. I mean, the fun thing about that is we can see the remnants today where the material is thrown out. We know how old they are because we have the records. Like to the day, we know how old they are, which really enables you to work out the evolution of that star over, because I say they fade over 3 months, but they still expand out. We can still see them for hundreds of thousands of years as this really hot gas cools off. And there must have been even more old ones that we don't know about. And so there must be other records possibly. And so that's always the fun thing. If we get access to new historical records where people have written things down, then we can go to them. But you're right, the Chinese are best at that.
Jan, it's been lovely talking with you. You know what? I think our conversation has shown that sometimes reality just kicks fantasy out of the park.
Yeah, that's true. I hope so sometimes.
Thanks for listening to this episode of Sci Fi Sci Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci Fi Sci Fact on the RNZ podcast page. RNZ podcasts are also available on Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.